Hello, everyone, and thanks for joining us. My name is Ali Al-Sharif, and I'm a steering committee member at ACE. ACE is a global community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We have a repository of YouTube videos that showcase authors presenting their research and practitioners demonstrating the use of emerging machine learning methods in the field. We also host social events where you get a chance to network and with fellow community members. We also conduct workshops based on helping participants take machine learning concepts from foundational theory all the way to fully deployed models. We have multiple streams organized around specific topics. This presentation is part of our machine learning interpretability stream. We encourage you all to subscribe to our YouTube channel and check out our website at ai.science. Today, we are hosting Zifan Wang. Zifan Wang is a first-year PhD student in electrical and computer engineering at Carnegie Mellon University. He received his master's degree in electrical and computer engineering at Carnegie Mellon and is currently co-advised by Professor Anupam Datta and Professor Matt Fredrickson in Accountable Systems Lab. Zifan's current research interest is building robust, insightful, and human understandable interpretation for deep neural networks. The work he will be presenting today will be based on his paper towards frequency-based explanations for robust CNN. This work is in the early stages of research and development, but he's going to give us a sneak peek today. Before I turn it over to Zifan, I will briefly share with you the motivation for why it is a very interesting presentation and a promising research direction. And that is computer vision implementations based on convolutional neural networks have been reported to be unstable and vulnerable to adversarial attacks that are not visible to humans. Think of an image of a stop sign where all you need to do to get a machine learning algorithm to classify it incorrectly is to alter a few pixels on that image. And these pixel changes are not visible to humans, but they are enough to get a machine learning classifier to incorrectly classify that image. So the explanation tools we have, such as saliency maps that highlight an area or a region of the image that are relevant in the prediction, essentially are not useful against those attacks because those perturbations are not visible to humans. So we will not be able to get insight from why the model was incorrect. The work that will be presented today is to help bridge the gap between human visual perception, and that is not sensitive to small alterations in the image, and the behavior of deep neural networks on an image classification task. The goal is to develop models that are robust to adversarial attacks. It is a very interesting presentation, and I'm looking forward to it. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So I will turn it over to Zifan. Please take it away, and look forward to hearing your presentation.
Hi, everyone. Thank you, Ali, and thanks for the invitation to the presentation. I'm very pleased to come here and share our work in the robustness and interpretations for deep neural networks. So here is our paper, and my name is Zifan Wang. I study at Carnegie Mellon. So this is a work in the progress, so we still have a lot of things going on, but we're going to discuss our initial ideas, motivations, what we have done. And again, thanks for hearing my presentation. So, okay, let's get started. So, firstly, like as Ali has suggested, like currently deep neural networks are founded to accomplish a lot of tasks in computer vision or language models, and they are very successful. They suppress a lot of traditional machine learning models. But we also found that you can use some well-designed and very tiny noise that applies to the image and will make the model just do not recognize the image at all. You can transfer a panda into a gibbon, which is found in Goodfellow's work in 2014. And so this paper is trying to understand or trying to answer the question like why a deep model is vulnerable to adversarial noise, and how can we improve the robustness of a deep model based on our understanding of why it is vulnerable. There are a lot of work has already done a lot of research in this area, and they also found a lot of interesting conclusions. But in our work, we're trying to answer this question from a fresh new perspective, the frequency response of the machine learning system to the input. So before we get into the detail of the frequency response, let's build some background of what is frequency, what is image, and what does it mean for a model to learn the frequency. So in the signal process domain, we have found that there's different ways to represent a signal. The first way is what we are usually use in machine learning system or for a human, or like we treat the signals as the different value at different times. For example, for one-dimensional signals, we can plot the value of each time. The y-axis is the time here, and y-axis is the value of that particular signal, like your heartbeat, like your phone signals. Also, for an image, it's actually nothing but a two-dimensional signal because each color is represented in RGB3 channels, and the value of color is just intensity of that signal. For example, we can just zoom in the cat, and you have found the cat is nothing but signals. So what the machine learning model really sees is not this colorful picture as we can as humans. They actually see a bunch of numbers. These are just the intensity of these two-dimensional signals. Here, this is a time dimension to understand the signal. But however, there is an alternative way to understand the signal in the frequency domain. And in my understanding, the temporal space and frequency space is just like the wave and the particle natures of a light. You can treat it as different views. So in a time dimension, we plot the signals of the intensity at each time step. But in the frequency domain, we kind of treat a complex signals as a linear combination of different multiple base signals. For example, here we have a very complex red signal here, but actually it is a linear combination by these three different base signals. And these three different base signals are nothing but just cosine signals. Therefore, when we use the periodic exponential signals as a base signals, this is nothing but just a Fourier transform. A short period will correspond to a high frequency, and a long period will correspond to a low frequency. As we illustrate here, we can decompose this very complex signal into a lot of exponential signals, and they all have different periods, which means they all have different frequencies. This Fourier transform really helps us in the signal processing because complex signal is very hard to deal with, but the base signals, the simple periodic signals, are very easy to deal with. So this is another way to understand the signals in the frequency domain. And a very simple example is, for example, if we have a signal S, and we can decompose it into two signals, A and B, and A and B just very simple signals, mean just two cosine functions. And they all have their coefficients alpha and beta here. The value of alpha and beta are usually treated as the intensity of this particular cosine signal. For example, if alpha is very big, then it's basically the major component of signal S is just the base signal A instead of base signal B. So this is for the one-dimensional signal. How about two-dimensional signal? What will the image looks like under the Fourier transform? Here we give a example here. So if we have an image of the dog and we pass it into the Fourier transform to see how it responds in the frequency domain, here is what we will get. We'll get a same two-dimensional plot, and in the middle, it is the intensity of the low frequency components, and in four corners here is the intensity of the high frequency components. And usually, in a usual way, human will more perceptional to the low frequency, no matter 2D or 1D. Like you cannot hear the ultrasound like a bat, or you cannot see those very high frequency patterns in an image. But on the other hand, you can see the dog and the grass and the tones. So they are all corresponding to this low frequency region. So that's why for error images, the intensity of the low frequency domain are usually high than the response for the compared to the intensity in the high frequency domain. So that's just a normally saying, but it's not always true for all the images. So this is what we are interested in, because we believe that the machine learning models may not only be perceptional to this for the image in the frequency in the time domain, they can also percept the frequency domain, because we believe machine learning models has a capacity to learn the Fourier transform and also to understand image in a Fourier domain. So here is our intuition to answer the robustness questions, because we found that if you input a image like this Pikachu with a lot of noises, human can basically ignore the noise and say this is definitely Pikachu, this is not something else. But if you input this image to a model, the model may not able to consistently predict this as Pikachu, and it will be distracted by these noises. But human will not distracted by these noises. It's like the model cannot ignore these noises, and usually these noises are high frequency or have very high component of the high frequency signals. So we're thinking maybe, so the hypothesis here is that the vulnerability of the model is because the model cannot ignore these high frequency noises, but human can. So if this is a hypothesis, then we can follow in this idea to say, if we can train a model which we teach the model to ignore the high frequency noises, high frequency components of the image, and only focus on the low frequency components of the image, will that make the model robust? This is kind of intuitive reasoning, because humans respond to low frequency, and we only want the model to respond to low frequency. If the model mimics the behavior of human, then we can make the model as robust as human. To verify this hypothesis, we need to verify, is the adversarial attack or the noises you generate to fool the model, is the adversarial attack always the high frequency noise? We take this question, and before we go into that part, to answer the question, is the adversarial noise always have a very high intensity of high frequency components? We have one trick. We have to apply one trick in our work. Previously, we discussed the Fourier transform, like we transform the image into this domain. But however, there's one disadvantage of directly using a Fourier transform, or practically we use discrete Fourier transform. It is because even you give the real signals, the Fourier transform may give you imaginary components, like the intensity is 1 plus 2j, something like that, and j is the square root of -1. Here we have a lot of imaginary components, and we actually do not want to deal with that. So practically, we use discrete cosine. Sorry, this should be cosine. We actually use discrete cosine transform instead of discrete Fourier transform. And the difference between the DCT and DFT is like, for Fourier transform, the base signals are all exponential signals. So it means it's a combination of cosine and sine in a real and imaginary domain. But for discrete cosine signals, all the base signals are just cosine signals. So here is the comparison between DFT and DCT. So in the DFT, the lowest frequency is squeezed in the center, but in the DCT, the lowest frequency will squeeze at the left top corner, and the right bottom corner is the highest frequency. So this is just a application trick. It does not change any theoretical analysis we have just formed. So it's just a trick here we want to bring up. In the all the following content, we'll use DCT, not DFT, because we don't want to deal with this imaginary components. Okay, here come back to our original question. Is adversarial noise always a high frequency pattern? To answer this question, we can directly apply the DCT transform to transfer the noise you actually add to the image to fool the model, and analysis its frequency component. And how is the result? Here we take a model, ResNet 50 model, and it's pre-trained on Zifan dataset, and we use the entire test dataset of Zifan dataset, and we pick 4 adversarial attacks that has been developed and verified is a good work. So here we have 3 Whitebox attack: PGD attack, CW attack, and the FGSM attack. So the main idea behind this attack is that the FGSM is like I set up a loss function. Like I want to minimize the loss between a target class, or I want to maximize the loss of the current attack. And I just using a gradient descent, and from the gradient, take the sign of the gradient and apply a learning rate, and I just add this noise. This is a noise. This part is a noise, and I add this noise into an original image X, and I form an adversarial attack. And the PGD attack is just doing the same thing, but iteratively doing multiple gradient descent. And the CW attack is just trying to modify, is using a new loss L to make the attack more smooth and more easy to attack. But that's not the focus of this paper. But I think if you are interested in this all attack, you may can take a look at the original paper. And the last attack we are focusing on is actually a black box attack. So original attack are all based on white box setup, because like you need the access to the gradient, to the internal component of the model. But this SimBA attack is a black box attack, which means you do not need any access to the model, to the internal of the model, to the gradient of the model. You just need the input and output. So we basically repeat this attack on the entire data set and transform the noise it generates into the frequency domain, and we average them across all the data set. And here is the result. So if you remember the DCT attack, the left top corner will be the low frequency part, but the right bottom corner will be the high frequency region. So one conclusion here is that we found like basically all this attack has all this adversarial noise has a very high intensity in the bottom region instead of the top region. So which means this all noise are trying to modify the high frequency component of the original image, and using this high frequency modification to fool the model. So here is a conclusion. Usually in the usually setup, you are more likely to find a high frequency adversarial noise than finding a low frequency adversarial noise. But I do know there's some work trying to generate low frequency noises to fool the model, but we just put that aside, talking about other more popular methods, PGD and CW attack. So here the conclusion is basically telling us if the adversarial attack is trying to target on the high frequency component of the model, but if the model does not care about the high frequency at all, for example, human do not care about the high frequency component at all. So it's like if you are targeting the high frequency component, but I don't care the high frequency component at all. Therefore, no matter how you attack the model, I shouldn't be changing my prediction at all. My prediction should be consistent because I don't care the thing you are trying to attack. Here is our formulation of that hypothesis. It's like we want a model on the left-hand side, which the high frequency component is the association between the high frequency component and the model's predictions are much, much weaker than the association between low frequency features with the model's prediction. But we don't want the model on the right-hand side, that the model's prediction is highly associated with the high frequency component and poorly associated with the low frequency component. If you have a model 2 like that, then the attack, because the attack is targeting the high frequency component, then the attack is very likely to changing the model's behavior. But if you are a human or you have the model one, then no matter how you attack the high frequency component, the model should be less sensitive to that kind of noises. The basic understanding, yes, the human lives in a low frequency world. We are not like bats. So then the next question is, how can we determine the association strength here? It's like I draw the arrow here, but the thickness, how do you actually determine the thickness here? If you are giving a model, I want to know how the association strength between a particular frequency feature with the model's prediction. How do you know the actual strength of these arrows? How do you know the actual thickness of these arrows? It's like where the model should be on this horizontal axis. We have the robust model, which only relying on the low frequencies, and we have non-robust model, which let's say this a extremely non-robust model, and which only relying on the high frequencies. And we all know that humans are more like to rely only on the low frequency. So it's like human are lying on the left side of this axis. But where the model is, where should we put this model on this axis if we're giving a new freshly trained model? It's like if we can determine where the model should be put on this axis, we can determine if the model is robust, and how robust it is by comparing it with the human's response. So the question here is come to how can we measure the association strength in a numerical way to make sure we put the model in a particular place, in a correct place corresponding to its robustness. So here comes to our another contribution of the work is like we develop a frequency attribution method to detect the robustness of the model. And before we enter into the frequency response, we firstly describe what is the attribution method is. So the attribution method is a method trying to assign scores to each features in the input. The higher score is, then it means this feature is more important. There's a lot of attribution methods in the area and trying to identify the important features for a given input. And our work is motivated by this occlusion method. An occlusion method is like how do we detect the importance of a particular feature? We basically remove these features from the image and we feed the ablated image into the system, and we observe the output change. If the output changes dramatically, that means ablating the feature causes a dramatic change to the output. That means this feature is very important, and this is the visualization of the occlusion. Basically, you can see the snake is very important because removing the feature of the snake will change the model a lot. So motivated by this method, we generate our occluded frequency method, which means if you want to determine how important a frequency component is, you can try to remove it. You can try to remove it from the frequency domain, and we transform it back into the time domain, and we feed the ablated image into the system and see how changed the model's response will be. And interestingly, we give an example here. The x-axis here is the frequency of the components. 0 means the zero frequency components, and 32 means the highest frequency components. Interestingly, removing the lowest frequency will not change the model's decision a lot, but removing frequency at the middle frequency region and the high frequency region will change the model's prediction a lot, which means the model's prediction are basically associated with the high frequency feature instead of the low frequency feature. This is not what we want. And we can actually visualize how the image would look like if we remove a particular frequency. Here on the second row, we remove the lowest 3 frequency. This is the lowest one. You can basically see if we remove this one, human can basically tell that this is totally different from the original image. But from model's response, model feel like they are actually similar. My prediction does not change a lot. But if you are trying to remove frequency with the highest attribution scores, human will say this is totally the same. But for models response, the prediction actually changes a lot. So model will say, no, this is totally different. And this is where vulnerability coming from. Model is using the high frequency component that human cannot notice. So model becomes non-robust. And to verify this idea is actually working for the all image and more models. We actually take some pre-trained models from Marjorie's group. They have some pre-trained models on Zifan 10 dataset using different adversarial training algorithms. And we here pick 3 robust model, and these are all trained with different adversarial budget. So these are the clean accuracy and the adversarial accuracy. But the high level understanding is like these models are more robust than the original model if you just train with cross entropy loss without any modification. These model are modified to more robust. And let's see the same thing on the frequency attribution for these 3 models. Here we have the curve of the NAT. NAT means natural trained model, which means the model is just standard trained. You don't use any adversarial budget to make it robust. And we have 3 comparison group. We have three members in the comparison group. They are trained with different adversarial budget, and we can see a very, very interesting and expected result. This is the same plot as the attribution, frequency attribution, as we show in this trunk example. So on the right side is a high frequency component. On the left side is a low frequency component. And the y-axis is a frequency attribution scores. Higher attribution scores means these frequency components are more important. Interestingly, for the natural trained model, the high frequency component is actually important. The attribution scores is not 0 at all. It's kind of very high. But for the robust model that we pick from Marjorie's group, their attribution scores at the high frequency components are basically 0, and the attribution of the low frequency features are non-zero. It's become higher. This is very interesting. It's like the robust model have a very weak association between the high frequency component, but the natural trained model have a comparably non-trivial association between the high frequency component. And we believe this is why the natural trained model is not robust, because the natural trained model have a thicker arrow between the high frequency components with the model's prediction, but a robust model has a thinner arrow between the high frequency features with model's prediction. So we can repeat this experiment for all the classes, and the results are kind of similar. It's like the robust model will have a low attribution scores in the high frequency region, and this is very interesting. Therefore, here comes the end of my presentation, but it's the third part, the last part in our paper we are currently working on. When trying to develop a method, like during the training process, we force the model to changing from associate high frequency features with model's prediction to associate the model's prediction with low frequency features. We don't want the model to develop a very strong association between high frequency component. We want the model to develop a high association between low frequency component. And if the model do have a strong connection between low frequency and the model's prediction, then the model is promised to be robust, because this is just like what human respond to the image. And thanks for watching my presentation. This will be the last slides, and I'll just hand back to Ali.
Thank you, Zifan, for that excellent presentation and very, very interesting work. I'm really happy that we had an opportunity for you to share this with us. I'm going to, this is the question portion of the session. So to the audience, please type in your questions through chat. And I also have a list of questions that were submitted to us in advance. So to summarize, maybe as a recap, your method is helping models ignore the noise in a similar way that human cognition filters out irrelevant information. So you're getting the model learning to more closely align with how humans learn and basically ignore input outside of a certain frequency range.
Yes, that's a correct summary. Thanks.
Okay. Now, would it be accurate to say that the way this work would be used is you're presenting guidance for improved model selection to help developers identify models that are vulnerable or that are dependent on this high frequency range and therefore would be robust, that would not be robust to adversarial attacks?
Yes. So we kind of trying to develop this way to help the developer to select the model, and we want you to select those models or respond more like a human. And how do we approach this? Is like we say like human lives in a low frequency world. So if the model want to mimic the human, then the model should only respond to the low frequency. Shouldn't respond too much to the high frequency. That makes the model become robust in a human's definition.
Okay, excellent. Now, we could potentially identify dependency on high frequency, or basically we can identify models that are vulnerable to adversarial attacks through other methods, potentially do some detect adversarial robustness through adversarial testing. Why would this method be more useful than just testing out models against a predefined set of adversarial attacks?
Yes, as you may notice, like when we take this model for moderate group, they already share their result of the adversarial accuracy. And the definition of adversarial accuracy is like you actually perform the adversarial attack with the same budget, and you do this for the entire data set to see how the accuracy will drop or how accuracy will change compared to the clean images. So this method actually requires the whitebox, access to the model. That you need the gradient, you need the ability to perform the attack many times, and you also need a back propagation because all this method requires the back propagation to compute a gradient to attack the model. But you also notice like in our method, we actually didn't require a white box setup. We just need the input and the output, and all the change is based on black box access to the model. We don't need a gradient, and we are only observe the frequency, so which means we don't need the back propagation. So the advantage is that firstly we are black box setup, and secondly, we do not need back propagation to solve the adversarial accuracy. So we believe we can make it more faster or more general for more models, because a lot of machine learning services will not open their port for you, right?
Okay, so it's model agnostic, it's less expensive, and then would generalize better. Essentially, are the three main advantages that I think I heard you say.
Yes.
Okay, now we have received an inquiry from an industry partner that is very interested in your work. Could you potentially maybe share with us what's next for you? How can people get access to potentially your experiments and be able to replicate your work? I know this is work in progress, but maybe can you help us, give us a sneak peek of what's coming next?
Yes, so we're working on to share the frequency occluded method, the code for this. This is not hard, so we're working on sharing it into an open source scenario. And for the rest of work, we're trying to develop this method in the training process to make the model have a high association between low frequency. So we assume that we can shortly make our work to submit it to some conference, and we're planning if we get accepted by the conference, and we're going to open source our result. So it's in the coming stage, and we're excited about that.
Okay, excellent, excellent. Well, again, this is a really excellent work, and I'm just going to go in and just do a quick check on additional audience questions. Here, I am just curious, when we refer to robust models, shouldn't we evaluate the model based on or beyond accuracy? So maybe I'll rephrase the question slightly. We're measuring accuracy metrics are well known and well established. What metrics would you typically use, or what you would use in this work for measuring robustness to adversarial attacks?
So usually we measure there's different ways to measure the adversarial or the robustness of the model, and one of the ways is get a very accurate sense of how robust it is by attacking the entire data set to understand the adversarial accuracy. So this is a very good method. It's a very good metric, but it's also expensive. So in our work, we will also do this metric as well. It's for certain because we want to get an accurate sense. But to get to this kind of a trade-off, like you want a less accurate sense of how robustness of the model is, but in the trade-off you can get a faster and you can get a more general method of answer if the model is like human, if the model is more robust. So in our work, except to the adversarial accuracy, we can also measure the contribution of each frequency. It's like if the contribution of the low frequency features is much higher and the contribution of the high frequency components is much lower, then we can basically conclude this model is much robust than a model have a very high contribution at a high frequency. So my answer is the contribution of the frequency components can also be treated as a metric to answer the robustness question, and we are working to deliver this in our paper.
Excellent, excellent. Just going to give it one more chance for any audience questions, and if not, we will maybe I can, Zifan, if there's any final thoughts or comments that you want to share with us before I will do a quick summary and wrap it up.
Yeah. So I think one comment is that it's very exciting. I see the community is trying to focus on the frequency domain in the robustness. I see a lot of excellent paper coming out in recent areas. It's not a comparative group compared to the people working on the time domain, the features as it is, but it's an increasing group. So it's very exciting. I feel like frequency components is fresh new, and we should pay more attention, place more effort in this area because it's kind of more interesting, more close to how model process the image instead of how human process image. And if we want to understand how the robustness of the models, we should approach the way the model analysis the image. So I'm excited to work in this area. Yeah, okay. Thanks.
Thank you, Zifan. Definitely really interesting work and a really interesting research direction. So I'm going to go in and just do a quick summary of the talk here, and that is computer vision implementations are based on convolutional neural networks are vulnerable to adversarial attacks, where small alterations to an image are essentially outside the range of human perception can cause a model to become unstable or lack robustness. To help solve that problem, Zifan and his co-authors proposed examining distribution frequency of the input space and demonstrated that for many existing adversarial attacks, the distortions are highly correlated with high-frequency components. And they proposed measuring the contribution of each frequency component towards the prediction, which helps us select models that are less reliant on high-frequency components in the input. Therefore, they would be more robust. Although we're able to detect vulnerability to adversarial attacks through adversarial training, the proposed approach in this paper is less expensive to accomplish the task, and it's generalized better because it is does not rely on access to the model, but it treats the model as a black box. To conclude, to see more free content like this, visit our website at AI and .science and log in to access slides from this and other sessions. Also, make sure to subscribe to our YouTube channel at ML Papers Explained to get notified about live sessions and other free content we publish. I thank Zifan and his co-authors for making their work available to us today through this session. And I'm very, very excited about this interesting research direction. And this concludes our event. And thank you for watching.